Okay, first of all, thanks the organizer for the nice environment and give me opportunity for present some works. Already Nilanjan have talked about this, how we can constrain the heating dynamics through GW, where the source is governed by the curvature perturbations. Here I specifically talk about the source that actually originated from the inflationary magnetic fields. Okay, so these are the summaries. Sorry, so not this is the content. So this is I give you the very basic about this, how why reheating is importance, and then go to the final results, how the gravitational wave spectral shape depend on the reheating dynamics as well as the inflationary magnetic power spectrum. Then give you some example how PTA data can help us to constrain those things, and then conclude. So when we look into the sky, then we observe that our universe is fully magnetized. Means very small astrophysical object like planet, stars, to very large astrophysical objects, galaxy cluster, every object have some magnetic field. The origin of magnetic fields is very difficult when we talk about the magnetic field length. Covering length is larger than kiloparsec and megaparsec scale. Existence of the magnetic field is not just strange things, but the current observational bound on this large scale, like kiloparsecs, the galactic scale and megaparsec scales, is very difficult to get without introducing any extra physics. So there is different models. So one of them are very useful model is the inflationary magnetogenesis scenario, where we actually introduce some extra coupling to break the conformal symmetry of the gauge field and produce the magnetic field. If the magnetic field really produced during inflations, we already gone different lectures, then it is a good source that can generate a significant GW. Okay. Now, why reheating is important? So because if we believe a standard Big Bang scenarios, so we have a phase where our universe expand exponentially. This phase is called inflations. So even if there is some radiation production during inflation due to the huge expansion, the temperature of the universe at the end of the inflations is quite low, almost zero. Again, we know that the Big Bang nucleosynthesis start at around 10 to minus 2 GeV scale. So if we consider the currently largest in energy scale that constant from the CMB data is around 10 to minus 5 MPLs. So this actually turns out the maximum temperature of our universe around 10 to 15 GeV. So there is a huge gap between these two, the maximum temperature and the Big Bang. So we typically believe that in between them there is a phase where actually inflaton transfer its energy to radiation and create the standard model particle as well as the beyond standard model particles. So heating is important because it gives you a proper initial condition for the Big Bang nucleosynthesis. Not only that, there is an extensive work on these dynamics. The heating can also be help us to produce the dark matter particles, and it also helps the present day relic abundance of the dark matter particle as well as the beyond standard model particles. Okay, it can generate the baryons, axions, so on. We already have shown that heating dynamics also influence the entire gravitational wave spectra. Even it can also influence the present magnetic field strength. Okay, so evolution of these magnetic field strengths also depend on the heating dynamics. So heating is important. So that's why we have to know how our universe actually basically evolves, particularly during this era. So how can we constrain those things? Already Niranjan have said that it is very difficult to constrain to CMB because the very nonlinear effect and very small scale effect, the heating actually play roles. So but GW actually after can easily probe the signature, actually carry the signature of the heating dynamics. So this is the few parameters that we have defined. So this is the main, the Kn, I define the largest mode that left the horizon at the end of the inflation, and the KRE, the mode that left the horizon when the reheating ends. Sorry, entered the horizon when the reheating ends. We parameterize everything in terms of TRE and omega. Alpha is the function of this. This is depend on omega. So if we know the energy scale of the inflations, then typically we can know what the value of the Kn once we provide the temperature of the heating and we provide the equation of state of the reheating dynamics. Theory only depend on the typical temperatures. Okay, so we can fix the Hn through these expressions. So throughout my result, based on that, we consider the tensor to scalar ratio is 0.036. That gives that maximum allowed energy scale of inflation, that is 10 to minus 5 MPL order. Okay. So now we go to the gravitational. So this is the well-known for equations. So I know this is the lambda. Lambda is the polarization index for electromagnetic field. It is very important because depending on the nature of the source, gravitational wave is also be different. So we can generate helical magnetic field. We can generate non-helical magnetic field. We have a helical magnetic field. Depending on the helicity, the gravitational wave also be helical. So that can be a crucial features we can observe from the direct detection of the B mode or direct detection of the gravitational wave. So we have a, if we detect the helical gravitational wave, so this is a clear signature that they can be formed due to the electromagnetic fields. Okay, so typically for electromagnetic fields, the source look like this. Okay, for rest of the talk, I typically assume that magnetic field is the dominated component, and whatever the production came from this electromagnetic field is governed by the electromagnetic fields. Okay, so our goal is to plug this equation in here and solve this equation using the Green's function method and plug it here and calculate the tensor power spectrum. So tensor power spectrum contain two components. One is the primary production that actually came from the quantum fluctuation, already is typically proportional to the energy scale square, is square by MPL square, and the second one is sourced by the electromagnetic field. So typically the power spectrum, if we for due to the electromagnetic field, can be expressed through these expressions. You can see this is the Green function. Okay, this is the function depending on the nature of the source. Either it can take this type of form or this, and the other the helical or non-helical information also encoded here, the source terms. Okay, if we have a helical field with a larger enhancement of the magnetic field, so typically you can say the tensor power spectrum proportional to PB square. So if you have a larger PB, so obviously the positive mode get more enhanced compared to the negative. So, and once if you provide me this, the behavior of the how the electromagnetic fields will behave, then we can plug it in this equation and solve this equation and plug it here to calculate the energy density. Okay. So there is a different way of generating the magnetic field. I mainly talk about the inflationary dynamics, where typically there is a specifically this type of coupling. Okay, so this coupling actually typically generates the non-helical magnetic field. This is provide the helical magnetic field, and for very specific type of coupling, Rath type coupling, then the generation of the magnetic field typically behaves like this. It's proportional to the energies, inflationary energy scale, and the power law behavior and Subhendra scale, and some dimension is constant. This constant depend on the nature of the coupling. It can carry the information about whether your field is helical or non-helical things. So now we plug it this expression in the previous this and calculate those things for different area. So now this is the general the source. So this is the first one is due to the quantum fluctuation generated due to the primary production. So already talked by this Sriram Kumar. Then when the mode are outside the horizon, they are flat. When they are inside the horizon, due to the reheating dynamics, they have changed their natures. Depending on the equation of state, they may be blue tilted, maybe red tilted. But when we go to the secondary production, so for simplicity, how the spectrum is behaving, so we break into two different regions for omega less than 1/3 and omega greater than 1/3. You can clearly see omega less than 1/3, the spectrum have only one spectral break, and the spectral break appears at around KRE. And when the mode are outside the horizon, then the zero spectral index simply governed by the magnetic spectral index. Okay, when they are inside the horizon, then they depend on both the magnetic spectral index as well as the equation of state, because n omega is typically governed by this equation. When we go to the higher equation of state, we see that there is a multiple spectral breaks. So there should be a clear signature whether our equation universe have higher equation of state or lower equation of state by analyzing the entire spectrum behavior. Okay, so here I actually choose 3 different benchmark points to see how the spectral is behaving differently. So first one is omega is equal to 0, matter-like behavior with some value, this dimensionless quantity, logarithmic scale, that the temperature, and we consider very large blue tilted because we try to feed with the NANO-Grav data. Okay. For omega equation state, you can see there is a flat region. This flat region actually came from the primary production. Then it goes due to the blue tilted spectral nature, and after certain time, after KRE, when the mode are entering, they again come down, and the nature is the red tilted. So there is a clear spectral way. When you go to the higher equation of state, you can see there is a multiple spectral wave. So that can be easily, depending on the equation of state, your entire spectrum are drastically changed. Okay, so we can be we can be constant from the delta negative bound. I skip this one. Okay, now if we plug this our model into the PTA data, we already have seen that omega less than 1/3 is more favor because they are consistent with the delta effective bound. If we go to this figure, you can go to the red line. It is continuously blue tilted and go and up and up. So it easily cross the upper bound of the GW predicted from the delta effective bound. So if we plug this in our model into the PTRK code, there with those very specific set of parameters, then we can see they can predict that lower equations. So you can see that the for all possible values of n, the lower equation of state is more favorable. Okay, it goes to 0, almost 0. Okay, now they predicted there's some heating temperature and some for very specific value of NB. Okay, so they can be well fitted when the NB is little bit large, because already the NANO-Grav data or PTA data, they actually predict very strong blue tilted spectra. So our model should be such that your GW spectra should be a strong blue tilted. So larger NB is more favor with zero equation of state. Why? Zero equation of state is actually free from both the delta effective bound as well as the tensor to scalar ratio. Okay. So here you can see that if we know the exact spectral behavior of the GW, using the data analysis, we can predict what would be the equation of state and how the initial spectral shape of the matrix generated during inflations. Okay. So these are the take-home messages. Okay, the GW really can help us to constrain both the inflationary magnetic field as well as the reheating dynamics. And this is the post-inflationary reheating dynamics also play a pivotal role for evolution of the electromagnetic field as well as the gravitational spectra that we already have seen. Depending on the equation of state and temperature, their shape drastically changes. And we already discussed that with a strong blue tilted spectra, it is possible to explain the current object data by the PTAs. I think, yeah. Thank you for your attention.
Thank you very much, Subhasis. I see a hand up there. Is there a microphone nearby?
So since retro type couplings typically tend to produce nearly scale invariant magnetic power spectra, and on the other hand, you are considering NB to be positive in this case. So I was just wondering if we need to worry about back reaction or strong coupling in this case, just out of curiosity.
Yeah, typically, yeah, it's possible. There is a issue with the back reaction, but when you go to the non-helical scenario, there is no such case. You can just alter the index, then both spectrum are the same. So there is no issue with the back reaction. So you can just go to the helical scenario, just talk this kind of coupling. Then I think there is no back reaction issue with this. And this coupling have a issue with the back reaction when you go to the positive end.
Just another quick question. In the total GW power spectrum, I guess you were considering autocorrelation between two primordial modes separately and two magnetically induced modes separately. So I was just wondering if there can be some non-trivial cross-correlation between these.
We already cross-checked. There is no such significant changes. The only changes, you can see that there is transition point. Like here, the primary one is dominating, then the secondary are dominating. Around this point, junction point, there is a certain enhancement. Otherwise, most of the cases, one of them are the more dominating compared to other. So not drastically change the spectrum.
That is at a much higher scale. I mean, that is at a much larger length scale than what can be detected, right? So it falls outside the detectable range. That's what you were saying.
Yes.
Okay. Thank you.
Any other quick question? There's one right there.
So already you have mentioned about the unknown reheating phase. So the duration of the reheating is unknown. So
Yeah.
then how is these results would affected by the duration of that? I mean,
Yeah,
if
yeah.
if a short, it's long. What
Look, like
happens?
for the let's focus on the NANO-Grav data like things. This is the scale where our mod are entering during at the end of the heating. So this is the KRE. So you can see if we have a blow tilted spectra, this continues to grow. So it should be come down, but otherwise it can break the delta effective bounds. And we already see from the spectral behavior, you can see here for omega less than 0, so less than 1/3, there is a only one spectral breaks, and spectral breaks appear at KRE. So you can see that if we detect this kind of spectral break, then we can easily detect what are the value of the KRE, and KRE is depend on the TRE. So in that way, we can directly measure the TRE. Now you have a question that okay, we have other reading temperature, different reading temperature. Then you can for this case, this is the different heating temperature, because here you can see this is 10 to the around 10 to the 4 GeV. Okay, so the spectral behavior shape is changed. Peak are appears in different frequency. So if we measure this peak, measure the spectral peak, then we can actually know about the heating temperature. Another things, your total energy, total produced GW also depend on the duration of the reheating dynamics. Okay, so comparing all this data, we can actually give you the information about what are the total duration of this period.
Okay, okay, thanks.
Thank you again, Subhasis. That was a very nice talk.